Most electronic devices are charged via a standard USB port. The USB port itself, though, can be powered in many different ways. It can be plugged directly into a wall socket, it can be part of a computer, it can be adapted to a car's cigarette lighter, or it can even be directly wired into a building's power system. Regardless of how the USB port itself is being run, from the electronic device's perspective, every USB port should be identical, and every USB port should treat your device the same way and charge it in the same way. That means that regardless of what circuitry is behind the given USB port, the port itself should have some sort of predictable behavior. There are many such examples of a resistive network containing independent and dependent voltage sources. And we want to connect a load resistor to that circuit, and we want to be able to predict how the circuit is going to react to that load, what voltage and current are going to be delivered to that load, and we don't necessarily need to know the details of what's going on behind the scenes. We just need to know how the circuit is behaving from the terminals at which we are engaging our load. If we want to make this a truly arbitrary load that could be any value, well, we know that the resistance could be anywhere from 0 to infinity. If we want to characterize the behavior of this network, we can characterize the behavior at these extremes. For example, as the load resistance gets larger and larger and approaches at infinity, this is an open circuit. This means that you have no connection, and essentially you have no load resistance connected. Then there would be an open circuit voltage that you could measure from the terminals of that network when there's no load connected. The other end of the spectrum is for when the load resistance is approximately 0. In that case, we have a short circuit where we have essentially a wire connecting the two terminals, and we're going to have some short circuit current flowing between those terminals. For any practical application, there must be a finite current flowing, and so whatever finite current is flowing must be slowed down by a internal resistance inside the network, since we're assuming here the wire would have effectively a 0 resistance to it. And so if we look at the open circuit voltage and the short circuit current, that gives us an idea of how the overall network is behaving from the perspective of these terminals, without us knowing the details of what's going on inside. A Thévenin equivalent circuit consists of a voltage source in series with a resistor. These are our Thévenin voltage and Thévenin resistance. This simple circuit connects to the outside world by two terminals A and B. If the behavior at these terminals is the same as the behavior at the terminals of some larger, more complicated resistive network, then we can use this equivalent circuit as a simplified model for a more complicated arrangement. In order for this Thévenin circuit to be truly equivalent to the other network, it means that the open circuit voltage at the two terminals has to be the same in both cases, and the short circuit current between the two terminals has to be the same in both cases. If we see the same behavior at these two extreme situations, then we know that the behavior will be the same at any other resistance between the two. If we look for the open circuit voltage is the voltage between terminals A and B when there is no connection between the two, when the resistance between those terminals is infinite. If there's no connection between the terminals, then there's no current flowing in the system, and the voltage drop across the Thévenin resistance will be 0. Then the open circuit voltage will be the same as the Thévenin voltage. If, on the other hand, we put a short circuit between those terminals, we'll have a short circuit current flowing in this case, because now there's a closed path for that current to flow. The short circuit current in this case is going to equal the total voltage in the circuit divided by the total resistance. Then if we want to know the resistance in the circuit, that would be the voltage divided by the current. This is an application of Ohm's law. A Norton equivalent circuit is a current source that is connected in parallel with a resistor and then connected to the outside world via two terminals A and B. We can use a Norton equivalent circuit to represent the behavior of a more complicated resistive network as well. If we want the Norton equivalent circuit to exhibit the same behavior as our resistive network, then again we need the open circuit voltage and the short circuit current to be the same for the terminals of the Norton circuit and for the larger network. If we see the same behavior for the maximum resistance and minimum resistance, then we know that we'll see the same behavior for all the other resistances between them. We can begin by considering the short circuit current, which begins to flow when we connect a wire between terminals A and B. In this case, our wire here has shorted out the resistance, so there'll be no current flowing through the resistor, and all of the current from the source IN is going to be our short circuit current. Thus, we know what our Norton equivalent current is for our current source has to be the same as the short circuit current. Then, we want to find the open circuit voltage. In this case, with an open circuit, there will be no current flowing through this branch of the circuit. All of the current from the current source will flow through the Norton resistance. And we know by Ohm's law that the voltage across that resistor will be the current flowing through it multiplied by the resistance. Then we can see that the Norton resistance would be the open circuit voltage divided by the short circuit current. We've considered Thévenin equivalent circuits and Norton equivalent circuits separately, but really they are two sides of the same coin. They are equivalent to one another because they're both equivalent back to the same resistive network. Both are just simple models representing the behavior of a more complicated system. They're also equivalent because we've seen how sources can be transformed from a voltage source in series with a resistor and a current source in parallel with a resistor. Thus, you can transform a voltage source into a Norton circuit and vice versa. You can convert a Norton circuit into a Thévenin equivalent circuit using the rules of source transformations that we have seen previously. And in fact, sometimes the resistive network will be simple enough that we can use a series of source transformations to simplify this network into simpler and simpler circuits to reduce it all the way to a single Thévenin or Norton equivalent circuit. We've seen thus far how to take a more complicated circuit and to reduce it to a Thévenin or Norton equivalent circuit by finding the open circuit voltage and the short circuit current. What we've seen thus far, you need both of those values in order to find the Thévenin or Norton equivalent resistance of the entire network. Sometimes it's simpler to find only the open circuit voltage or only the short circuit current and then find the Thévenin or Norton equivalent resistance directly. When you have a network that contains only independent sources, like we have here, you can simply deactivate those sources to produce a simpler circuit, and then you can find out what the equivalent resistance is as seen from the two terminals of our circuit. This equivalent resistance is going to be the Thévenin or the Norton equivalent resistance. Recall that if we're deactivating independent sources, to deactivate a voltage source means that the voltage source has voltage. To eliminate a voltage source, we want zero voltage, which means we want wire, which is what we have right here. Similarly, if we want to deactivate a current source carries current. If we want to deactivate the flow of current, that means we need an open circuit. And so this current source here would just be an open circuit with no current flow. Once you've deactivated the the sources, then you can find the equivalent resistance, and you can use that for your Thévenin or Norton equivalent circuit. If you have a network that contains dependent sources of either kind, it's a little bit more complicated to find an equivalent Thévenin or Norton circuit. Let's say we wanted to find a Thévenin equivalent circuit to this network right here. We would need to find the open circuit voltage, so that would be our Thévenin voltage. And then we would want to find the Thévenin resistance as well. But since this is a complicated circuit, it might be difficult to find the short circuit current. What we could do instead would be to deactivate the sources. That means we would deactivate all of the independent sources, and we would turn our voltage source into a wire, just a short circuit, here on the right. However, we can't deactivate our dependent sources. Those have to remain. But since we've deactivated the independent sources, there's nothing left to drive these dependent sources. So what we have to do is to apply a test voltage, Vt, at the terminals of this circuit. And then we want to measure what current is flowing from that test voltage. The ratio of the voltage being applied divided by the current that is actually flowing as a result is going to be the equivalent resistance between those terminals, and then that equivalent resistance will be our Thévenin or Norton resistance for the circuit. Similarly, you could use an arbitrary test current IT, and you could calculate Vt and find the equivalent resistance. To summarize Thévenin and Norton equivalent circuits, you're going to take a more complicated network that's connected to the outside world by two terminals, and we want to reduce that to a Thévenin or Norton equivalent circuit. We can do that by finding the open circuit voltage and the short circuit current, and we can use those values to find the Thévenin voltage or the Norton current and whatever resistance we have for our circuit. If we have an even more complicated network where we have dependent sources, we can still find the open circuit voltage, and we can still find the short circuit current. And that will still give us the same Thévenin and Norton equivalent circuits. This is probably the most complicated way, but also the way that always works. If you have a simple circuit network that has only resistors and independent sources, then it may be possible to use a series of source transformations to find the overall Thévenin or Norton equivalent circuit. So for example, here we have a voltage source in series with a resistor, so these two can be combined and converted into a Norton equivalent circuit. We can simplify what we have, and then we can take that simplified circuit and convert it back into a Thévenin circuit so that we can combine the resistors. Once we have a Thévenin equivalent circuit, it's one more source transformation to make a Norton circuit. If you wish to find the Thévenin equivalent circuit of a network that contains only resistors and independent sources, then the Thévenin equivalent circuit can be found by finding the open circuit voltage and then eliminating all of the sources and finding the equivalent resistance as seen from the terminals. If you want to find the Norton equivalent circuit, you can use the same method, but in this case, you would find the short circuit current instead. But again, as long as there are only independent sources, you can deactivate all of those sources and calculate the resistance directly. This resistance, as seen from terminals A and B, is both the Thévenin and Norton equivalent resistances. If you have a circuit that contains dependent sources in it, then you want to first find the open circuit voltage or the short circuit current, depending on whether you're looking for a Thévenin or a Norton equivalent circuit. In this case, if we're looking for a Thévenin equivalent circuit, we would find the open circuit voltage. Then we would deactivate all of the sources. We would deactivate that voltage source and turn it into a wire. And then we would have to apply a test voltage here, and we would want to measure the test current, and we could use the ratio of those to find the equivalent Thévenin resistance of this circuit. Similarly, we could also apply a test current source and measure the voltage to find the equivalent Norton resistance of that circuit.